So the discovery of electrons led to more questions such as these. There must also be positive charges in the atom, so how do the opposite charges fit together? Are atoms a jumble of even more fundamental particles? How many are there? Are these individual particles solid spheres? Do they have some internal structure? Does the electron have particles inside of it? Lots and lots of questions. So Thomson, the guy who discovered the electrons, came up with an idea for what the atom might look like. And this is an example of, a good attempt, but it turned out to be wrong. It's called the Plum pudding model. He was British, and we don't have plum pudding in the United States. Think of it like a blueberry muffin. So the blueberry muffin model of the atom. So the electrons are like the blueberries in the muffin, and then there's this sphere of positive charge. He didn't know what it was. There's something positive. We call that the muffin, and that's what it's like. You gotta start somewhere. So that was his idea. Well, you don't just have a hypothesis and you test it. So before we can talk about how it's tested, you have to learn a tiny bit about radioactivity. So we've all heard of radioactivity. We know that it's not good for you, right? What is it? It's the emission of small energetic particles from the core of certain unstable nuclei. It was discovered at the end of the 19th century by Becquerel and Marie Curie, also known as Madame Curie. They did not create radioactivity. Radioactivity is a natural occurrence. But using radioactivity, we're able to probe the structure of an atom and learn a lot more about what's inside. So there are three main types of radiation: alpha particles, beta particles, and gamma rays. And the ones we need to just have some clue about are the alpha particles. The alpha particles have a positive charge, and they are the largest of those three. If you're curious about radioactivity, come back for Chem 1B, and in chapter, I think it's actually chapter 22 now, we'll talk a lot more about it. It's pretty interesting. Okay, so Ernest Rutherford had worked under Thomson, and he was doing an experiment to confirm this plum pudding or blueberry muffin model. He was not trying to show up Thomson, he was just trying to show that it was correct. So in this experiment, he took these positively charged alpha particles and aimed them at a very, very thin sheet of gold foil. And the plum pudding model would predict that the particles would just go straight through the foil. So that's what he was expecting to see. So here's a schematic of the setup. Here we've got our source of alpha particles shooting this beam of positively charged particles to this really thin gold foil. And then there's this detector set up around so that we can see where they end up. Most of the particles did go through the foil, and that was expected. But some of them were deflected, essentially bounced back. And that was not expected. About 1 in 20,000 bounced back. Rutherford said this was about as credible, about as believable, as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. 15-inch cannonball, say, at a piece of tissue paper, fired at great speed. What's it going to do? It's just going to blast through the tissue paper like there's nothing there, right? Nope, sometimes it's going to bounce off the tissue paper and hit you in the face. That would be surprising, right? So this was shocking. Why are some of these particles bouncing back? There must be something else going on in here. So he came up with a new model to explain this. Here's the plum pudding blueberry muffin model. Those alpha particles should just go straight through. This is a sphere of positive charge, and then we have these little tiny electrons. They're too small to deflect these particles. They would just go straight through. But the actual result is that while most of them went straight through, a few of them bounced back. They must have hit something that was quite massive. And so he concluded that the that matter is not as uniform as it appears. There must be large regions of empty space dotted by small regions of extremely dense matter. And so we now call this dense matter part the nucleus. And in the nucleus we have the protons and the neutrons, and so this is called the nuclear model of the atom. So he developed nuclear theory, 3 basic ideas here. Most of the atom's mass, all of its positive charge, are contained in a small core called a nucleus. Most of the volume of the atom is empty space, throughout which tiny negatively charged particles are dispersed. Those particles are the electrons. There are as many negatively charged electrons outside the nucleus as there are positively charged particles inside the nucleus. So we have equal numbers of positive and negative particles, which explains why atoms are neutral. They don't have a charge. The positively charged particles are called protons. So this model was very successful, but there was a little problem with it. So hydrogen has 1 proton and helium has 2 protons, but if you look at the mass of those atoms, the mass of helium is 4 times that of hydrogen. And if you think about a box with 1 bowling ball and another box with 2 bowling balls, and this box weighs 4 times as much as the first box, it doesn't add up, right? So there must be something else going on. Rutherford and one of his students, Chadwick, figured out that unaccounted for mass was due to neutrons. So these are neutral particles that are inside the nucleus. They don't contribute to charge, but they do contribute to the mass. So neutrons have no electrical charge. They are neutral. So the names here are suggestive. Neutron, neutral, right? Proton, positive. So the neutron is similar in size to a proton, but instead of having a positive charge, it has no charge. So this explained the discrepancy they saw between hydrogen and helium. So the hydrogen atom has 1 proton and no neutrons. Actually, let me draw a picture here. So here we have, there's hydrogen, 1 proton. Here's helium. In its nucleus, there's 2 protons, and there's 2 neutrons. Each of these squiggly circles has the same mass, and so this one weighs 4 times as much as that one. And that explained the problem that they saw. So the nucleus is extremely dense. I mean, we can't even get our minds around how dense it is. Over 99.9% of the mass of the atom is in the nucleus, and yet it occupies very little space compared to the size of the atom. So we can think of this as a little bit like clouds or fog that we're very familiar with. So electrons are like the little tiny water droplets in fog. They have negligible mass, but they're dispersed over a large volume, and because there's so many of them over this large volume, they prevent you from seeing, right? Because they get in the way. Each little tiny water droplet is nothing. You could see, past that, it's just a little tiny speck, but there's so many of them and they occupy a lot of space. So even though fog is mostly empty space, it keeps us from seeing. Matter is much less uniform than it appears. So if you look at the bench top, it's this shiny black, weird black surface that they use in all chemistry labs. And it looks, pretty uniform and consistent, right? Well, that's because we're backed up so far from the individual particles, like standing way back from that Lego Taj Mahal, the details of the individual blocks blur together, and so it looks like it's smooth when it actually isn't. So just here are a couple of mind-boggling ideas. If you took a bunch of nuclei, well, no, that's later. This is a different one. If the nucleus was the size of a period, so on your printed page, the size of a period, if that was the nucleus, then the electrons in that atom would be 10 meters away. That's 10 yards, right? That's 2 yards. So like way over here. So here's a period. That's where all the mass of the atom is. And the closest electron is way over there. What's in between? Nothing. Empty space. If you were able to take just the nuclei without all that extra space and put them together and make something the size of a grain of sand, that grain of sand would weigh 11 million pounds. It's really dense.
So there is a concept then of nothing.
Mm-hmm.
It exists?
Yes, nothing exists. Yeah. There's actually a lot more nothing than we're aware of. Yes?
Are we going by the German definition of nothing?
I don't...
It can't be measured or defined. Meaning, is it possible that there is something between those two that we just haven't been able to perceive?
It's certainly possible. It's certainly possible. And that gets to the point that in science, an established model or a law is the closest we can get to truth. And at this point, we know of nothing in the nothing. But is it possible that there are smaller things in there? It's possible. We're just not able to detect that yet. But you think about the air in this room. You know, what's in the air? What is air? Well, it's a gas, right? It's actually a mixture of gases. There's oxygen floating around, which is good because we're all breathing that. And there's carbon dioxide because we take in the oxygen and our bodies transform it and do stuff with it and make carbon dioxide and we exhale that. And so there's some water vapor because there's some humidity and there's a lot of nitrogen gas and then there's traces of other gases. Little teeny tiny atoms floating around, but what's between them? Nothing. Empty space. If we took some scaffolding, this reminds me of the old metal jungle gyms, we called them, when I was a kid. Just super not safe. They're made out of metal pipes, probably lead, and then underneath was asphalt, right? Great. People fell and landed on their heads all the time. But you climb on these things. So this is like, one of those old jungle gym things. Scaffolding, and imagine that it's the size of a football field and it's 10 stories tall. I mean, like, this is some massive jungle gym, right? It's mostly empty space, right? There's these individual metal bars that are holding it together, but most of it's just empty space, air, right? Now, if you looked at that from an airplane, and here we're getting a little bit of that perspective, as you back up from this, all these lines begin to overlap and you lose the resolution. It appears solid, and yet when you zoom in on it, you realize it's mostly empty space. That's how matter is. It looks solid to us because we can't resolve the differences between the empty spaces and the not empty space. So when you knock your knuckle on the table, you can't do that at home because every time you make a knocking sound, the dog goes nuts because that means somebody's at the door, right? So we never do that at home. You knock on the table, that's like taking one giant scaffolding, your knuckles, and crashing it into another giant scaffolding, the table. They don't go through each other, but they're mostly empty space. Any questions? Things are not as they appear.
What we see, is that the electrons or that's the electron part of what we see, right?
What we see, I believe, is light that's reflected
Also,
from the surface of atoms. Yeah. Because the atoms themselves are too small to see. But they do reflect light. And that they reflect and absorb light, and so they reflect some colors and absorb other colors, and that's where we get colors from.
I think he's asking, like, is the light reflecting off the actual cloud, or is it reflecting off the nucleus?
That's a good question.
I had a individual who was doing it. He made a joke saying, "Hey, I won't hit you," and he held up and hits me. And I was like, "Ow!" And he's like, "I didn't hit you because there's the electron cloud between my hand and you, so technically I never touched you."
Yeah. Well, that's a little bit like, setting off an explosion with a shock wave, and the shock wave can knock down buildings. But I didn't touch you with my bomb, right? Yeah. Those are interesting questions, and a lot of them I really don't know the answers to. And it's ideas like that lead people to do experiments and to find out. Yeah. And of course, in today's world, many of these things have already been studied. And so you don't actually have to learn how to do an experiment like that and get all the equipment. You can hit the internet and look up what other people have done. And that generally is the first step in scientific research. You've got an idea, you look and see what other people have done, and you might realize, oh, well, that question's already been answered. But if it hasn't, then the information you get from other people can help you devise a better experiment.